Hi, everybody. Let's take a look at air pressure. So, we've talked about this a little before, but we're going to really formally go through the fact that air pressure as we go up in elevation changes and it gets less. The most air pressure would make sense would be closest to the ground because you've got the most stuff stacked above you. And you can kind of see that in this drawing here. If we're down here at sea level, all of the atmosphere is above us, just like when you're in a swimming pool. If you dive to the bottom, you can feel a lot more pressure on your ear because not only do you have the whole atmosphere above you, now you have that 5, 6, 8, 10, however many feet deep your pool is that you're swimming in, all of that water above you as well. And remember, we really live in a sea of air. It's a fluid. Water is a fluid, but gases are a fluid as well. And the more pressure they have on, the more closely compacted they are together. And you can see as we go up, with less pressure, they can spread out farther and farther. And so as we increase our altitude, we decrease our pressure. And that's what this graph is representing. Pressure increases at the same time altitude decreases, or as altitude increases, pressure decreases. So let's see what that means. As we look at this and we try to look at the atmospheric pressure, if we get to the top of Everest up here, we're going to have a hard time breathing because the air is not so close together at this point that when you breathe in, it feels like you're getting a full lung full of air, but the molecules are farther apart and you're not getting in nearly as many oxygen molecules as you would if you were down at sea level. And that's why if you're up in like a Boeing 747 or a big jet plane, it has oxygen masks in case there's depressurization so that you can get in enough oxygen as they quickly then hopefully descend the plane into an altitude that's better for us to breathe. So that's why we've talked about this before. If you climb a mountain like Mount Everest, a lot of people bring oxygen, canned oxygen, to get enough into them. It takes so much energy that once they use a can, they don't want to carry it anymore, so they throw it off to the side. So Mount Everest is littered with trash. The other problem is if you happen to perish while you're climbing Mount Everest, it takes too much energy to bring you back down that becomes your final resting place. So you will also find people who didn't make it down up on Mount Everest still as well. And that's because there just isn't enough air pressure to hold the molecules close enough together to get your oxygen in. Also, as we look at this, different altitudes change the surface pressure on our like water. So at sea level, water boils at 100 degrees Celsius or 212 Fahrenheit. But notice as we increase our altitude, our pressure changes, and that also affects the boiling point of water. So there's two ways that you can make water boil. You can increase the temperature until you get to like 100 degrees C if you're at sea level to get the boiling point of water, or you can go up in the atmosphere and then you don't have to heat it to quite as high. Because look at this, at 6,000 feet, you only need to be at about 93 degrees Celsius. So that's kind of like that mile-high city. So that's why Denver has really the Denver omelet. You can only get in Denver because there's less pressure pushing down on those molecules and the gas bubbles can get bigger. And so you get really fluffy egg whites. But it also means it's much harder to boil something. So there's tricks that you have to do with high altitude cooking that you don't have to do where we are. We're only a couple hundred feet above sea level. If you get to 10,000 feet, you're all the way down to 90 degrees. And if you're where an airplane flies and you weren't pressurized, it would boil at 79 degrees C. Now, luckily for us, that airplanes are pressurized, so if they want to boil water, they only have to get it to that 100. So another way to think about this is air pressure is all around us. For every square inch on our body, there's 14.7 pounds of pressure. So every square inch has almost 15 pounds of pressure. So it pushes on me this way, and it pushes on me this way, and this way, and that way, and basically all around us. In fact, we're pressurized for that. That's why you have to wear pressure suits if you go into outer space, because we need to keep that pressure. Otherwise, we have issues with our blood where gases will start to come out. If we take the pressure off our blood vessels too fast, we get something called the bends if we're scuba diving and we go really deep, and then you have to actually stop every 10 meters or so for so many minutes to let the gases escape from your blood system so that they don't rupture. Otherwise, if you go up too quickly, you get something called the bends, which is decompression sickness, otherwise known as you will get really sick or could die. And they want to, if you survive it, And then you have to go into a hyperbaric chamber and they have to repressurize you and then slowly bring you out. And quite often they'll do that a number of times. But air pressure is all around us. So that's why we have a skeletal system, because we have to be able to survive that pressure. And our, our skeletal system was designed for our pressure. And if we weren't, we'd be just a big, we wouldn't have the ability to stay upright. Like a slug doesn't have a skeletal system, so it stays lower to the ground, and it's kind of spherical, except for it's on the ground, then that part's usually pretty flat. So our skeletal system allows us to adapt to this pressure too. So pressure is a big deal. The farther we are down on the ground towards the sea level, the more we have stuff stacked above us. Kind of like this person here. Down here, there's lots of weight on that person, versus up here, there's not that much weight that you'd feel. And you can feel a difference. You can feel that if you've ever, like I said, dived to the bottom of the pool, you can feel the pressure on you. This is an old drawing kind of showing that, that problem. One thing that happens is Denver has a really good cardiovascular unit, because a lot of people have heart attacks. My uncle did when they went into Denver, because as the pressure goes off you, sometimes it allows clots to flow through in the release. And so they are known for that. The other thing that can happen that can be a problem, like let's say you're skiing, is if you were to rupture an eardrum. So that's why they say you shouldn't fly when you have a cold, because you don't want to rupture that eardrum with the pressurization and depressurization of the cabin. A friend of mine's sister was skiing in Denver and had gone up, and as they came down the hill, her eardrum ruptured, and it was really sad because she couldn't leave that pressure zone until the eardrum healed. So she couldn't go up the mountain and she couldn't go down the mountain. All she could walk is kind of like an even path all the way around, because the eardrum was so sensitive to that pressure. So what is pressure? Well, we can have buildup of pressure with carbonization. You guys know this. If you shake up a bottle of pop and then open it, it's going to spew everywhere, or can. You can have also, if you have champagne, which I don't usually have, but I have a picture of it because, well, it's a great representation of something under pressure. So barometric pressure, we usually express it in inches of mercury. The rest of the world would say inches of Hg, which is mercury but in grams. It can be expressed as 29.92 inches of Hg, which is average pressure. Actually, we call it Hg. It's torr, or millibars in metric. Sorry, should have read farther down. So millimeters of mercury is torr, or 760 torr is the average. We still go with Hg. Mercury is 29.92. That's our average pressure. So remember how we did isotherms, which is equal areas of temperature, and isobar now is equal areas of pressure. So pressure maps show us how close those gradients are. So if you have really tight isobars, really tight variation in pressure, it's going to be super windy, because everything wants to go from high pressure to low pressure, kind of like a waterfall. It's not going to flow up the hill, it always flows down the hill. So the weight of all that molecule above us, remember every square inch is that 14.7 pounds per square inch. That's a tremendous amount of pressure on our body, and we're designed for it. Atmospheric pressure is measured by a barometer, and you can have a mercury barometer or an aneroid barometer, and we can have spring barometers. We actually naturally adjust our pressure in our ear. That's why when you get sick, sometimes you get an earache, because your eustachian tubes, the tubes going to your ears, if they get plugged, you can't actually equalize the pressure. So that's why if you're getting on a plane, it's always a good idea to chew gum or have some hard candy or something that you can force yourself to swallow, so that you constantly equalize the pressure. It's why you sometimes feel your ears pop. And sometimes if I'm kind of like right on the verge of getting sick, as I drive home from Mound to Bloomington, there's that huge hill in Eden Prairie, and occasionally, if it's just the right set of combinations and pressures outside, my ears will even pop going down that hill. But always in a plane, my ears pop. And that's because our ear is trying to equalize the pressure inside of our ear canal to the outside. And if we take a quick look at this, this is showing that equalization. And if you want to look at this on your own, you can. I am not going to turn the volume, but I just want to show you what happens. As air pressure goes in, the inner ear has to be pressurized. And this is that tube that we were talking about that goes through and allows air in and out. It's called the eustachian tube. And if it gets swollen, it can't allow air pressure in or out to equalize. And so if we go in a little farther, let's say it's 760 torr out there, but now this is going less. Now this pressure is higher and it's going to bulge that out. And then this is going to open up and let some pressure out. And when that happens, then we get a great enough pressure, it should open and release and let some of the pressure out. There it goes. And the opposite will happen too. So if this continues to drop, it will let more and more pressure out. If we go the other way, however, now the pressure outside of our ear is increasing, then it pushes our eardrum in, and then as this opens, it actually lets air through our nasal passages, because remember, all of this is our sinuses, our nasal, our tear ducts are all connected. So as this happens, as the pressure increases out here, then this will allow air in to equalize the pressure. The problem is, if we end up with, and I think that's going to stall on me, if we end up with this being inflamed and you can't pressurize, then as the pressure out here increases, it's hard, and as the pressure out here decreases, it also allows that to expand and you get a really severe earache. All right, so one of the things we can do, and if I were in class, we would take a pop can and we would do this experiment. So I'm going to show you some videos of it. And what can happen is, think about this, as I heat water inside a can, all of that air in there expands, and fast moving air moves fast and starts to flow out. You can see the steam going out. So if I were to really quickly put a cap on it and hit it with some cold water, now all of that hot air inside the can is going to condense, and there's not as many molecules in there as there were to start with, and it will actually crush the can. We'll do it in 9th grade, so don't worry about it too. But this is what happens. Basically, take that, we heated it up on the stove and flipped it upside down into cold water, and the air couldn't suck in, or the water couldn't suck in as fast as air could, and it crushed the can. And it even works with 55-gallon drum. Same thing, they heated it up and then they put a cap on it and then sprayed it with water, and you can crush that can. You can even crush air tanks, or sorry, train tanks. That's atmospheric pressure. They literally pumped the air out of it and the atmosphere crushed it. One of the things that's really fun to do is to see what happens with basically a vacuum chamber. And we can take water in there and we can actually take the pressure off, and you can see the water start to boil. But the easiest way to see it and what happens is put in a bunch of marshmallows. And as you take the pressure off, that's the top video, the gas bubbles inside start to expand. Now it's interesting, my nephews went to Wayzata, and I think it was in 6th or 7th grade, they had to do a scientific method experiment where they created everything from scratch. Well, they happened to have a science teacher for not, so guess what? They came to my classroom and we did the experiment. One did friction with surface, so we did a water slide in different fabrics and see which is the best if you wanted to go down a water slide to get you to go the fastest down the slide. My other nephew, my youngest one, he wanted to know which would be the best marshmallow to roast, which would get the biggest if you're roasting it. So we bought a whole bunch of different marshmallows, and we measured them before and at their biggest point, and then how much they compressed. We found out is the cheaper the marshmallow, the more air it's composed of, and the more air pockets means we got bigger marshmallows. So what's happening in here is we take the pressure off. All of that gas trapped inside the marshmallow is trying to expand because it doesn't have so much pressure holding on until it ruptures the membranes. And then what happens is when you put the pressure back on, there's not that much gas left inside, and you shrink all the marshmallows into tiny little things. So density is expressed in grams per cubic centimeter if it's a solid. If it's a liquid, it'd be grams per millimeter. Because, okay, I'm going to geek out a little bit on you. How we figured out what a milliliter is, we took a cube, under the interior was 1 centimeter by 1 centimeter by 1 centimeter, and filled it up with water. And we said that 1 cubic centimeter, then, that volume, is equal to the liquid volume in milliliters. So 1 milliliter is equal to 1 cubic centimeter. And density is mass divided by volume. You're going to need this in 9th grade, by the way. That's why I'm kind of pre-teasing you with it. And temperature is affected by density. Really cold air is packed tightly together, and that makes a big difference. Where hot air, really hot air, that can spread farther out, and because of it, it's less dense. So hot air is less dense and it can rise, and we get convection currents going. So as that rises up, it cools, and as it cools, it sinks back to the ground where it gets heated back up, and then we can get these convection currents going. So cold air is dense and sinks. Materials contract when they're cold. Warm air is less dense and rises. It expands when it heats, and then we can get these handy dandy convection currents, and that's a big item to understand. If you can't hear or understand this, I would like you to go back and watch this video, because it's pretty important that you should take a listen. I'm going to try and play it here and see if we can't get you to get through it, because I'd like to talk about it as we go. Maybe.
Let's compare the density of these 4 solids and these 4 liquids. Cork, oak, ebony, a lead sinker, vegetable oil, water, carbon tetrachloride, and mercury, which I've already poured. Did you know doctors measure the density of urine to diagnose some diseases? I thought you'd like to know. Makes for a good party icebreaker. Okay, how about this one? Mechanics measure the density of the battery fluid to check the car's battery.
So now they're putting vegetable oil on top, which should be less dense so that it's going to float the layer up. Now that mercury is so dense we can't have that in school.
Here's the question. In what order do you think these solids
Dr.
will
Bailey
arrange themselves
from
in the
Grey's
jar?
Anatomy. Very
Go
young.
ahead, guess, while I drop each one in.
So that lead sinker is actually going to float if you look really carefully on top of the mercury.
Ebony.
The wood's going to go up the next kind of sink, because that means it's less dense than the one below it, but more dense than the one above it. And so you can have solids and liquids all floating at different levels according to density.
Just seen and heard, estimate the density.
So this is where I would say, where would you see this in practice? Well, if you like salads and you like a vinaigrette salad, which is oil and vinegar, you will know that it will separate out, and you need to shake it up before you serve it. Otherwise, it's separated and you're just going to get vinegar, you're just going to get oil, which is not as good. So things will tend to separate out by densities. So here's a trick. Warm water is less dense than cold water. So if you ever taken a bath and all of a sudden your bathtub gets cold, and then you put in more hot water because you're trying to warm it up, and then you have the little overflow, well, you're letting all the hot water out through the overflow. So the trick is actually to drain some of the water out, because the cold water will have sunk to the bottom and it will flow out the drain at the bottom, and drop it about an inch or so, then reseal it, and then put your hot water in so you don't lose it through the top drain, because you want to get rid of the cold stuff from the bottom before you put warmer stuff in on top. So that's a density trick if you like a bath. All right, so now you're going to go to some questions, and they go with that video we just watched. So I will stop this on the Edpuzzle and I will ask these questions. Are you ready? Rank the following according to their density. Which is the lightest, the least dense on top, and which is the most dense on the bottom? Now this question will come up in Edpuzzle, so you'll answer it there. The next question. Which is more dense, warm air or cold air? We just talked about that. Which is more dense? And if you guessed cold air, you're right. Cold air is more dense than warm air. Which is more dense, oil or water? Which one floated on top in that video? Water is more dense than oil. Oil will float on top of water. Which is more dense, water or wood? Which one floats? Well, the wood floats, so water is more dense than wood. And this is talking about that friend of mine, Sister Sharon, who couldn't walk up the mountain or down the mountain because as she ruptured her eardrum, she had to stay on this equal pressure line. And that pressure line that we're going to lead into the next thing is called an isobar. So this is practicing just like we did isotherms, but with isobars. But these usually have tenths, because remember you said it's usually like 29.29. And sometimes you could get to 30 and sometimes you could get to 28. But for right now, we're going to say it's all the same whole number. We're just going to look at our decimals. So let's look. I've got a 29 here. And remember, we don't have sharp lines. And I'm going to find my next 29. And here's another 29. Now, if I was going to do a key, then I should be putting that this is 0.29. My next line, if I'm going to color code it, let's say is green, we're going to say that's 0.30. And that will be my green line. Okay. Now let's look. Okay, I've got a 30 here. So I'm going to say I'm going to go there, obviously, because that's the next line I'm going to do. But I can't find a 30 between 32 or 33. I can't find one between 31 or 32, but I can find a 30 between 29 and 31, right there. And I can't find a 30 between 31 or 32, but there happens to be a 30 here. So we're going to take that line, and that's my 30. Now we need to do 32. All right, so between 31, sorry, I should do 31 next, shouldn't I? Sorry, not thinking. We'll do 31. So between 30, we're trying to adopt a cat out that is a stray. So that was a quick call on that. Sorry about that interruption. So we're going to find 31. So now the interesting thing is I look at this, 30 and 33. There should be a 31 and a 32. So I'm going to go ahead and mark my 32 to begin with. Now my 31, there's a 31 here, and between 30 and 32, there should also be a 31. So I'm going to go ahead and mark my 31. And I kind of missed that, but that's hard drawing here. Sorry about that. And hopefully you can see yellow because we're going to do that for 0.32. And so 32, we've got those lines, and those are called isobars. Isobars connect lines of equal pressure. Okay, now in a really great world where we were all in the same room together, and you're not trying to watch this at home, I would have you draw isobars, but instead you're going to have to learn how to read and interpret. So this would be the one that I would normally have you guys do on paper. And we're going to start, you'll notice these are all in the 30, so by 10, 15, 20, 25, 30. And this would be the one that I will have you do. Now I'm going to go ahead and fill this in, and then we're going to talk about it. Okay, so this is a really rough, quick rendition. I didn't get all of it done, but I did do a bulk of it. And what you're going to notice is, here are my 40s. Here's my 35 right here. And this is 30. And do you notice how they tend to circle in on themselves? And these lines cannot cross over one another. I can't have a 40 go down to this 40 because I can't find a 40 between 35, 38, 38, and 39. That's why I circled this around this 40.2 and this 40.3. So there's a 40 line there in between these. And here there's a 10, a small pocket of lower pressure, and then pressure gradually increases. And what's interesting, if you look here, look how far this gradation is from this isobar to this isobar. That means since it's a shallow gradation, you're not going to have as much wind. But look right here, these lines are super close together. If you're anywhere in here, you're going to be experiencing a big change in pressure, and everything wants to go from high pressure to low pressure. And because of that, that means you have this high, densely packed together air flowing into this less densely packed air, and it's the closer the isobars are together, the stronger the winds. So if I have isobars really close together, like this, super windy day. But if they're like this, not so windy, because it's got much more distance to travel before it equalizes out. Kind of like think of a water balloon popping. It's under pressure inside the balloon, but the second you release the pressure, it flows out in all directions. And the greater the amount of water in the balloon, the quicker it's going to release out, or the faster it's going to want to get out of there. Think of it that way. It's not perfect, but it's a pretty good analogy. All right, so as we look at this, this would be the final thing that we would look at on these notes, and we would have done this together physically in class if you happen to be in the classroom and you're not watching this because, we're not there. But I do want you to take a look at the fact that isobars measure areas of equal what? Pressure. The closer isobars are together, the faster or the slower the wind. Okay? So, isobars measure areas of equal pressure, isotherms measure areas of equal temperature, and the closer the isobars are together, the stronger the winds. If you have questions, as always, ask. That's what I'm here for.